propagating from this place to that places. So this is what did they do? When you move here, it carry the energy. And the wire one end and it flip, the flip-flop like this, and it travel just like what I showed you. That means a energy is being traveled. Okay, so a disturbance is propagated. So it's something like this. It's propagated from one end to another end. So we like to ask us a question. The question is, when you're doing such motion, what is involved? One is related with displacement. Displacement is vertically. Another one is related with horizontally. It means related with x coordinate. Then the next one is hidden some places, because when you travel like this, depend on each time, the displacement are different. So consequently, the disturbance is in this kind of disturbance is related with two coordinates, related with two function. It has two independent variables. So y is a function of displacement, is function of two variables, in which case y xt. Y is a function of x and t. And then you can do it in another way. This when you're referring back, this is equal to a function. This function, how you're going to represent it, that's what we're going to look for. How we can represent a wave propagation function describing this. So there's one is go forward, another one is coming back, so that you can represent it in the following. Can be represented as a function of x, and then function of minus vt. This is what they propose, or a function of x plus vt. Okay, this is what they propose, two-way to handle that. So before we are doing that, we like to somehow draw the wave function, the wave model. So the wave model is something like this, is like that, this is x, okay? And we have something like this, y, and we have something like this. Basically, as soon as we drew like this, we already propose the wave function can be represented as sine wave, using sine function to represent it. Then we like to say the period. The period is for this y of travel from here to here is called a period. When come a cycle, t is a period. Period is when you travel to a complete cycle, and the times required for that. So after we're doing this, then the traveling wave have all these different functions to be representing. Long time ago, we do the spring action, and we do the what we call another one on chapter 12 is related with pendulum. So in those in the spring action, spring motion, we basically propose that they basically omega x is basically is equal to a times sine 2 pi divided by lambda x. Okay, so something like this type of it to do. In this cases, we go through another type, situation. This is only for x dependent. X dependent. What happened for the time dependent? So for the time dependent is related with velocity. Velocity. So in that cases, we like to second guess what is the best way. So if it is related with time, then the variable may be, remember, if we in sine, this is a angle or in the radian. This information is in radian. So the time is related with what? The time must be related with velocity. Velocity times time give you a distance unit. And distance divided by a lambda, in which case converting to radian again. So the second guess is if you represent this function in time, then it's a times sine of 2 pi lambda times v times t. So if it is time dependent variable, there's 2 pi divided by lambda times v times t. So in which cases, we try our best to guess what function that is. But this is called educated guess. And then we like to combining all this information into one equation, one expression. In that cases, we like to say y is equal to 2a times sine 2 pi lambda x minus 2 pi lambda v times t. In these cases, the wave function is this both dependent variable x and dependent variable as time t. So in these cases, we like to say that is equal to a times sine times 2 pi 2 pi lambda times x minus vt. Okay, by simplification. So by working on this, then we know that v as far as speed goes is equal to lambda divided by t. T is a period. Lambda is a wavelength. So if we divide by t, then equal to the velocity it travel. So if you guess on this, 2 pi lambda we want to express as k. And then we like to express 2 pi divided by capital T is equal to omega, or equal to 2 pi f. So we finally have a very good representation by this wave function, in which case is equal to y equal to a times sine kx, kx minus omega t. This is a representation of wave disturbance through space, both between the dependent x and not and dependent on time. So from this function, we like to find the differential equation to represent a wave function. This wave function turned out to be a very important function. It's called the Maxwell development, called Maxwell equation. So all this, we will try to prove that is true. So on next day, tomorrow, we will touch basis on this, finish this 13.3 section tomorrow on to developing what is the differential equation for this wave function. To identify what the k is, what is v is. So k is equal to the wave number. Preferably say is angular wave number. That equal to 2 pi divided by lambda. And then the omega is equal to 2 pi f. And this one we make a mistake, and this is omega t. So if you do all this carefully, all this whole thing is in radian, because omega is in terms of radian per second and radian. So this one again is a radian function. So we get a function nicely represent a traveling wave. So we have to say if it's a wave function, in a particular cases, is related to oscillation. So